Let's look at how computers represent numbers. We'll start with decimal. Decimal means 10. The decimal number system is what we grew up with. We learn math with this system. It is a base of 10. The numbers used in this system are 0 through 9. Let's consider that we have 3 slots. From the right, we have the ones, the tens, and the 100s. We have a 2 in the 1 slot, a 3 in the 10 slot, and a 7 in the 100 slot. To determine the value of this number, 7, 3, and 2, we take the 2 and we multiply it by 1. Then we take the 3 and we multiply it by 10. We take the 7, multiply it by 100. We add the 3 together, 700 plus 30 plus 2, to find the value of 732. We're going to apply this same strategy to binary numbers. While decimal meant 10, binary means 2. It's a numbering system with a base of 2. There are only 2 numbers in this numbering system, 0 and 1. Looking at the very far right slot, it is 1. Our next slot, which is in the middle, is 2, and our slot on the left is 4. These are multiples of 2 because we're working with a base 2. We begin with 1, and then 1 times 2 is 2. And 2 times 2 is 4. Now let's calculate the value of our number, 1, 0, 1. Starting from the right, we multiply 1, the value, times our slot 1. Then we take our slot 2 and we multiply the value 0 times 2. Then in slot 4 we take the value 1 times 4. We add the values together, 4 plus 0 plus 1 to get 5. Binary numbers are usually 16-bit or 32-bit, not the 3-bit we saw in the earlier slide. From the right, the slots begin with 1 and are multiples of 2. 1, 2, 4, 8, 16, 32, 128, 256, and so on. The slots from the right can also be thought of in terms of powers. 1 times 2 to the power of 0 is 1. 1 times 2 to the power of 1 is 2. 1 times 2 to the power of 2 is 4. The calculation is the same as demonstrated on the previous slide. Multiply the value of the bit 0 or 1 times the slot and then add all the values together. So the values from the far right, take 1 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8 plus 1 times 16 plus 0 times 32 plus 1 times 64, and so on. There again, you could also use the powers. 1 times 2 to the power of 0 plus 0 times 2 to the power of 1, and so on. You might like thinking of it as 0 and 1 refer to the states of off and on. If 0 is off and 1 is on, you count the slots that are on. Negative numbers have a 1 in the far left bit, the most significant digit. The far right bit is the least significant digit. It can become cumbersome to calculate because a 1 in this digit requires at least one very large multiplication. There is a shortcut. First, you negate the number. To negate the number, Reverse all the 1s to 0s and all the 0s to 1s. So the 1 became a 0, the 1 became a 0, the 0 became a 1, the 1 became a 0, and so on. Then add 1 to the result. So here I added 1 to turn the 0 into a 1. Now this value is the same as the original value, and it will be easier to calculate. Another data representation is hexadecimal. It's base 16. 16 is a multiple of 2, and it's a natural fit with binary. The numbers are represented with numbers 0 through 9, but we run out of numbers, so we use letters. Hex 10 is A, hex 11 is B, and so on. Let's convert 15 from digital to binary, and then to hexadecimal. The binary value is 1, 1, 1, 1. 8 plus 4 plus 2 plus 1. And the hexadecimal value is F. Let's convert the decimal value of 4. Its binary value is 0, 1, 0, 0. Its hexadecimal value remains F4.